need to increase a bit the size of the font on my console here, or are you okay?
Today I have a 27-inch monitor, so I'm good.
Everybody's good. Okay. I'll just make it a little bit bigger. Okay. Good. Okay, so this is another session about integrated model in Rust. So we had a few of those already because there were a lot of things to learn. There's a lot of new concepts that um, the framework is exploiting, is using here to make it work more efficiently. So we start by going through a bit the actor model and how we use that and we base our framework on that. Then we went to go through how to how the actors are implementing and defined in our implementation and how we initialize the actors. And then in the section after that, we went to look in more detail at the input and output, how it's implemented, and how then we connect an output of an actor to an input of another actors, and how it's implemented, and how this implementation allow us to check through the type system that the rates are matching, the type of the data is matching, and so on. So we went through that. And today we're going to look more at running a model, how we run the actors and run a model, and how that is implemented as well. But before starting, if there's any questions regarding the previous session, that something you want to have questions or you want more information?
No questions.
If not, let's get started. Okay. So this is the simple example that we are going through. So we went through this part here where we define the actors first. So in the simplest example, we have a source, a filter, and a sink, which is collecting the data. So this is the three actors here that we have, and then in the previous session we see how we connect them within that. So it's always the same pattern where we add an output and then we connect to one or multiple output. I realize there's something which is missing here. I don't even know it works. It should be multiplex. If you have more than one it goes after that. Add output gives builder, and then you specify the parameters after that. So yes, if you connect one output to multiple input, then you need to specify to multiplex it. Okay. So we saw that last time, and now we're going to focus on that, how we make a model and how we run it. So the model is just a collection of factors. And the actors have already been defined with their client inside and the connection from one to other ones. So everything is set up. We just need to run each actor. Each actor is independent, is asynchronous. So we just need to start a thread and with the actor running in its loop inside. And then just wait for the source to be exhausted, and then the source will be dropped first, and we have the cascade effect where one by one all the actors that connect to the source and the next actor to this actor will also drop, and then the whole model will nicely shut down that way. So that's why. So you can start each actor by hand yourself, but the model structure is a convenient way to put all the actors inside a vector and then use some methods called on the model to use it to check the model to make a graph of the simulation and then to run the model. You see that when I create a new model instance, I pass a vector and I have to put all the actors into a box because again, each actor has a different type, and normally you cannot create vectors of different type. So in fact, what the model expects is a vector of a threat object, as I explained the last time. And that's what allows us to put all that together like this. So I was just saying that what the model is doing is putting an actor in a thread, and this thread running the actor loop. So I think we can spend some time first understanding the actor loop, because it's really what's at the core of the. Okay, I'm sorry, I'm going to have to close the door. So let's look at the loop in
Was there a dog barking? Because I didn't hear anything.
no, my wife arrived and she started to make some noise and dog, but not my wife, but and so that's why I decided to close the door. Okay, so. So this part here is really you see, starts the actor infinite loop. So this was an actor. You run a loop forever, unless it receives an error message, which tells him that a disconnection has happened between one of the other actors is connected to, and it will nicely shut down itself. So if we go through that, so we may have or not inputs or outputs. You have at least some input or some outputs or both. So here we check if we have both input and output. And if we have both input and output, depending on the input and output rate, you may be in a case where you decimate or upsample the signal. So if you let's take an example, maybe to fix the idea. So imagine your simulation is sampled at 1,000 Hz, and your input is at 1,000 Hz. So that means that NE is 1, but you want your output at 100 Hz, then you have your output rate at 10. The rate are always the frequency of your simulation divided by the 1, right? So we are in the case where the output rate is larger than the output rate is slower than the input rate. It's that way. So it corresponds to that case here. So when you do that, the loop is going first. You're going to collect your input for as many times as the ratio of the two rate, and then you're going to update your state. So this is useful, for example, when you want to simulate an integration on a camera, for example, Because update is where you're going to create a new frame and add it to the one. So if you have a camera which take an input at 1,000 kilohertz, and then you decimate it at let's say one hertz every second, then you're going to like this be able to add 1,000 frames together, right? And then when it's done, then you're going to call this function distribute. In fact, and the distribute method, it's going to call the send method on the output, and remember the send method of the output calls the write function of the client. So like this, what happens is, if we take an example of the camera, here we add the frame, and here, because we call the output, the send method on the output, which calls the write method on the client, we can read out the detector and add noise at the end, for example. And the collect here is a method which goes through the inputs and read the inputs. And the inputs which are read also are used by, you call the read method of the client to update maybe the data in the client as well. So this first line here reads the input, and the input are passed into the client. Here you can update the state of the client, and here you send the results to the outside world. Okay. And this is the same loop. If NO and NI are the same, then the ratio is 1, so that works also if they are the same, right? Okay. So that's the decimation, and so and if there's no integration like a camera, but you just want to decimate a signal, like every 1/10 input you want to pass it as an output, then that behave like a simple zero order old. No, it's not. It's a decimation, not a zero. It's not the order old here. It's a decimation, so you just take it 1/10. The other situation is when if you want to go back. So if we look at our example here, if we now we have an input which is at 100 Hertz, and you want to go back to a kilohertz output. So here your output is going to be equal to 1, that your input is going to be equal to 10. So then we are in the case where the output is less than the input rate. So it's this part of the loop. And what we do here is that we first collect all the inputs. And from the input that are collected and we assign to the client, we update the state of the client. And for the ratio of NI to NO, you send the same output on again. So this is the zero order old. This is how you upsample, right? So you're going to hold the same value for this ratio. This is how you upsample the signal. Does that make sense?
Yes, I have a question. What determines the height of an actor? Is it the input rate or the output rate? For example, in your first example, we have 1 kilohertz as the input and 100 hertz as the output. We are going to run the code inside of the actor in 1 kilohertz or in 100 hertz?
It's the input rate. If you think about the rate being the rate at which we update the state, it's the input rate. If the definition of the rate of an actor is the rate at which you update the state, it's the rate at which the update method is called, and it's always the input rate. You see here, for example, we have the update in the loop, because and here we don't have it here. So, make sense?
Yes.
Um,
And I
how
think that I agree that this is the correct way.
Mm-hmm.
how
Okay.
hard? Sorry, how difficult would it be to replace the zero order hold by a first order hold? So it just kind of.
Yeah, that's a good question. It's you cannot do it inside this generic framework, but I did it for example, the win loads, which are at 20 Hz, and I want them at 1 kHz, so I didn't want to have big step. So I have a first order hold, and you implement that in the client. In the client, you can implement that, because remember, so taking about the example of the win loads. The win loads is just okay. I will come back to the example of the win load and try to answer that at the same time. But the short answer, sorry, is you do that in the client. So the actor framework provides the simplest mechanisms to upsample, which is a zero order hold. If you want to do other type of sampling, you have to implement it yourself in the client right now.
Okay, could there be a special upsampling client or something like that? Just like an extra block you just put in between, and then it'll smooth basically.
Yes.
Okay.
We could do that. You can define, yes, we can have generic first order hold client, for example, but we'll do that. We'll take, it will take a zero hold.
It wouldn't be able to do it on the first time step, but then once there's two, it could just like extrapolate.
Yeah, it's what I was saying. If you do a generic one, you introduce a delay because you cannot do it the first time. So whereas when you do it in the client, like I do it in the win loads, I have my full series. So I use one step before to get from the very first sample a value. Whereas because first order hold, you need to know both value of the interval. So you can do it you can do it. I think you can do a generic client for a first order hold, but you probably will have to introduce a delay in the system.
Yeah, I don't think you have to have the delay, but you could just be extrapolating.
Or you extrapolate.
Yeah, you can't interpolate because you don't know the next value, but extrapolate you could, and I mean maybe sometimes that would not work in your favor, but
Yes. But you see, when you start to think about interpolation, higher orders than the zero order hold, you have all these possibilities extrapolated, and you can extrapolate forward or backward as well. So it becomes a bit of choice of the developer. So if you make something generic, it's a bit of work to allow all these different possibilities. So for now, it's left aside. If somebody needs it, then he can implement it.
Okay.
This is what I did for the WinLoad client. Where the WinLoad client is a good example because it's an initiator. There's no input. There's only an output. So, and you see, in that case, how it's implemented, you just update your state, and then you send the output. There's no input to receive. And it's in the update that I do the first order hold. So if I take at most 400 seconds of data, but I know already the sample before because it's already by sequence. So I don't have to extrapolate. I can interpolate backward, in fact, and move like this. So that's so it depends really on your application and what you may know a priori from your signal when you do a first order hold to improve it. So that's why there's no generic for that first order hold. And then you can have a terminator as well, where you have, so basically it's when we log signal, there's no output, there's only an input. So here, we update the state. No, sorry, we collect first, of course, because there's only an input, so you collect the data first, and then if need be, you update the state. Right. Yeah, for the logger, for example, I fill buffers where I put the data. Yeah. Update is optional, so depending on your application, you may just update the state through the read or write, or read and write function if you have both sometimes, because both give you the possibility to mutate the state of the actors. But so update is optional, but I still have it implemented here because sometimes it's a bit cleaner when you have a complex client to have a read just to read the input, write just to write the output, and update to update the state. But sometimes you may want to skip the update functions. The update is implemented per default on the client, and it does nothing per default. It's just there, but it does nothing. So okay, so that's important to understand the sequence and the loop, because it's really how the system works. So, and when you are in a loop, as the destination of sampling, so the loop is going to always to wait at collect. If the input have not been sent already, then it's going to wait, and then so it's how the synchronization between the actors happens. Whereas on the distribute where we send output, you can specify if the size of your mailbox, and it's the size of 1. So that means it's going to send only one element and wait next time. But if you can have a variable size or unbounded size, then going to send this data and fill the mailbox. So if it's a size of 1, if it's a size of 1, it go back up, and then it will wait. It will wait here until the client has received and read. If you say unbounded, for example, it will never stop at distribute. It will send and then go back. So in some cases, it's also useful to have a loop that never stop at distribute. It just send and then go back and then.
Can you repeat this part?
Okay, so I was saying collect there's always a stop at collect. If it's always wait to receive the data. If the data has not been sent already from the actors, if the mailbox is empty, it will wait. Distribute, so send an output to a mailbox which has a size of one message, right? And after that, it continue, collect, go back, and send the next message if the mailbox is empty. That means that the client had the time to read already the message. If not, it will wait for the mailbox to be empty and send again. Okay, that's the default behavior. So you wait at collect, you update, and then you send the output and into a mailbox with the size of one message, and then you go back and then you wait for the next box to be empty before sending the new message. Okay, but you can when you define your output, you can specify the size of the mailbox, or you can specify the mailbox as being unbounded, so infinite size. So in that case, you will when you send your output, you will never wait for the mailbox to be empty or to have enough space. It will always fill the buffer and send it. So it will go collect, wait. Does that make sense? Okay.
I have a question. So if one of your actors or clients was just a game, and you put that in there, would that then have a sampling rate? And so would there always be a delay associated with that game?
There's
or
no
would
delay.
It be instantaneous?
No. It will be instantaneous first, no, because you will put the same rate, NI and NO will be the same. So you will be in that case here. where the loop is in fact is one step because the ratio is 1. So if there's no delay, you just collect. You may want to update, but maybe not. You just want to pass again and then distribute. Okay? So there'll be no delay here. In general, there's no delay introduced in this loop. Only the client may decide to hold the value one sample time or 2 or 3 and then send something else anytime. But in the actor doesn't introduce delay, except when we explicitly bootstrap an output.
But the client would introduce a delay?
It can. It's a developer choice.
Okay, it can also be no delay. Okay.
Yeah, exactly. It's your choice. For example, the control system that Rodrigo is delivering to me, some have delays, and that's the client, but the actor doesn't have. Except, effectively, I was saying, when we do bootstrap. So where is the bootstrap? Bootstrap is somewhere. Yes. You see, I have also this function bootstrap. Let's go back. Yes, we will see that. We'll come back on that. So let me double check. Yeah. I'll show you the bootstrap function here. So I have also a bootstrap function which just check if there's some output, then it will send the output immediately. So in fact, so I show you the run and the bootstrap function, and what happened is so the bootstrap function do 2 checks. First, it checks if there's some outputs, otherwise there's no point of bootstrapping anything. And the output have a flag called bootstrap. And if it's true, then it will send an output, otherwise it won't send it. Okay. So I will show you the model now. In the model, when we start the run of an actor, first we call bootstrap. If this actor has some output flag at bootstrap, it will send something, and then it will run the loop. So let's go to the model now. Unless there are some question about the run and bootstrap thingy.
No, any time in the future, I'd like to come back to this because about the bootstrap, but it's more related to the study that I'm performing with the simulations than related to the code. So I think that we can move forward for now.
Okay. Yeah, we can always come back to see them. But it's important that we all have an understanding of how the sequence of action, because when you analyze a system and it behaves a bit differently to another implementation, we need to understand that. So the model. So here I explain how I define the model by creating a new model by putting all the actors that the model is going to manage into a vector. I need to box them because they have a different style. I won't go back on the threat object. You can read that on your own online. There's sort of detailed explanation. I touched this concept on last week. And the model. Once you have the model, you have all these functions here. Model name simple. So let's go. Let's first take the most important. Talk about the most important function, which are check. So here, the model we use the compiler to do a lot of check on the model, but we cannot check everything, or maybe we can, but the model the framework will become too cumbersome. So here it performs some extra check. For example, if you set so an initiator and a terminator have respectively the initiator have its input rate to 0 because there's no input, and the output, and the terminator have the output rate to 0 because there's no output, right? So if your input and your output rate is different than 0, it's expected that you have some inputs or some outputs, right? So some of the checks that the model does, it look at the input rate. If they are non-zero, you look if there are some input or some outputs, and if they are not, then it will stop the simulation and will tell you that the kind of check it can do. And then you run it, and then you wait. There's an interesting thing here, because this sequence is mandatory. You check, you run, and you wait for the model to complete. It seems obvious, but sometimes at the end of the day, when you put your model together, you will be tired and you may make a mistake, and then you can end up with something like that. And if you do this kind of thing, and you try to compile, it will say you will have an error. Yeah, method not found in those cycles. So that's something else you can do with the compiler is to have a state variable where you keep track of the state of your system. And if you do put back on, yeah, that works. You can keep track of your system, but the state variable is a type parameter. So at compile time, then it will tell you before you start running. And we can spend a bit of time in time we left before I show you the model how you achieve that.
Quick question.
Yes.
So when the function that's called run, is that basically start?
Yes, it's start. Okay. It's where you will first call the bootstrap method. That is for the outputs that need to be bootstrapped, there will be. And then you start to call the other run method of the actors where you start the loop.
If it's always the same sequence, would it make sense to just have one function that is, I don't know, a new name that just
you could
play?
Yes. you can say play, yeah. Go. Yes, you could. Yeah, yes.
I had one more question. Maybe it's not really related to Rust, but so when you run it, is there a way to know like where the bulk of the computation happens? Can you profile where you spend your resources?
So there's some profiling tool, third-party tool, which come with Rust that you can install and check that. I'm not sure how that works in an asynchronous environment, computing environment. But so I use it. I've used it for single-thread application, and it's very useful. It works. In a multi-thread application, I don't know what it's going to report, but maybe it works. I didn't look at.
Maybe it's more trial and error. You add something and see what happens.
Yes, but there's also in Rust I mentioned the test section of the project. There's also a benchmark station, where you can run some tests. So it's kind of test, but specific, and it computes the time of your function. And if you combine that with a third-party software called Criterion, which is a free software, it will also create the database. So you can see, make sure that if you add new features, if it's going to have an impact on the time or not. So there's some profiling tool, but there's also this built-in benchmark tool that you can use. Do that. Yes, it's in terms of project management, it's quite sophisticated. You can do with cargo, but a lot of features available to us. Yeah, so for the model, yes, you could have a single function, but it's for sometimes you want to be able to split. It's also useful to do that and to make sure that you don't do any mistake. Especially, I often split here myself. So I do that like this, and then later I do model weight. Because sometimes now I have a first model, for example, which is going to run just with the wind load to wait for the frame to stabilize. And then because a client from one model to the next in the same application keep their states remain the same. So I can transfer a client from one model to the next. So then I have a next model which do all the control loops with my client. But before running this next model, sometimes you need to compute calibration matrices or to initialize the atmosphere and so on. So what I do sometimes, I create the model here, and here I do all my calibration while the first model is still running and finishing. And then when I finish my calibration, I force a wait here, and then I start the next model. So that's why it's split like this. But yeah, we could have a single function because many times effectively, what did I forget here? Oh yeah. You could have a function which does play, like you said, everything.
Yeah, I mean, now I understand better why it makes sense to keep them separate, because like it seems like the wait function basically then nothing else happens right until it's done,
yes,
right?
Exactly,
Okay,
exactly.
yeah.
But sometimes, because remember when you run, you have as many threads as actors, and they're completely run independently of this thread where your application. So you can start to do other things, but then at some point you want to go back to the original model, so you need to wait. So that's why it's like this.
If you wanted to rename a function, for example, if you wanted to rename run start, is that easy or is that very tedious to do in Rust?
It's easy. It's easy. You just need to modify add a method to the model, and have this method called run, and then that's okay.
Oh, okay, but there isn't an automatic way where like you change something, all the references are changed as well. Okay.
No, there's no alias for methods. There are alias for type and not for method, for example.
Okay.
So if we look at, so it's interesting to understand, I think, from a conceptual point of view, how you can have a state variable which is a type parameter conceptually, such as you aren't sure that methods are run in a given sequence, and you cannot mess up with that otherwise. So I'm going to show you that now. That. So imagine we have our structure. This is slow. Oops. Doesn't answer to me anymore. It's back. Okay. Group struct model, and we want the state to be a type parameter. So we define a generic type like this, and we have some data here, and here just for that. And so this state doesn't hold any data. So you don't. But when you define a generic type, it needs to be associated to a field, even if it doesn't really manipulate any data. It's a requirement of the compiler. So we can define a state variable inside, and we're going to call it phantom data of such state. So that tells the compiler that this when you compile this state, you will throw it away. It will just help the compiler to create a sequence of byte code necessary in the right order and doing the check. But at the end, you don't keep it, throw it away. So it's really something which is transient, I would say, just temporary. So once you have that, let's define our state. So like we do for the type of the data that we exchange from actor to actor, we can define empty variables. So for example, we can start with an unknown state. So we can create that. We can then, once we checked it, we can say, okay, we're ready. And then when the method, and then we can say, okay, when we run the model, we can have a running state. And then when done, we can say, okay, it's done. So we can call that completed state. So this is the fourth state of a model, for example. So now you go make your implementation, such as you can run some method in one state and in the other, and transition from state to state. So the initial state is the unknown state. So we're going to make an implementation for unknown. And we can do a function new, and it's where we define our model. Here will be data, like F64, right? Just for this example, so we create a new instance. Sense. Again, tracking data. So you see, you can you define your structure with a generic type, which is your state variable, but you define your implementation with a concrete type that you specify. That means the new method exists only for a model in the unknown state. You cannot use it for ready, running, complete, or whatever. That won't work, right? And then after, and to transition to another state, for example, if you want to do some check, and the check, and if they are successful, you go to the ready state. So what you do in that case, you do model ready. And so let's say you perform some checks, and I'm going to write it. And then once and when you've done your we have to pass self because we're going to consume it. And we're going to make a new version of the model, but with this new state, and you just copy the data over after the check. Oops. Yeah, like this. Okay, does that make sense? You see how you can define methods that belongs only to a concrete type for your generic structure, and you can transition a structure from one step to another by rewriting putting the same structure but with a different concrete type as for the generic type ready. So that means that now that we are ready, we can move to the running to running the model. So in that case, you can do a new implementation, but in that case, for model ready, where we can have here a function called run, for example. Oh, prefer start. Let's call it start. Self. And then when we are here, it will be running. So we're going to have an output will be the model of running. And then here we do starting stuff. And at the end, you do redefine this model in the running state this time. And will be the same thing. You see?
Yeah, I'm like.
How you can.
I feel like maybe a minute ago I finally started understanding what's happening. So I think Rodrigo already has it, but just for myself. So you're basically defining 4 different kinds of models, and it's kind of like a generic,
yes,
like a short
yes.
notation, but Rust will think there's 4 different kinds of models, and then you have this shortcut notation where it allows you to basically, for each of the 4 models, you define a or you can define different functions for different types of models.
Exactly.
Okay.
Yeah. And you're totally right. It's when you define a generic type, when you replace your generic by a concrete type, like here, that type that here we have defined, these types are really unique and different. The compiler doesn't mix them up. So it's by using this feature of Rust, which I've already mentioned as monomorphization, then we can transition from state to state. It looks like you have the same model in different state, but in fact you are really different, going from one type to the next, to the next, to the next.
If you wanted now to define a function for all of them, that's the same function? Or
so if you want to
for 2 of them, is there like a notation for that?
Yes, let's see how you can do that. So if you want a function which functions for all of them, you can define using the generic notation. So model function affect all. ASAP, sorry, je vais passer référence, par exemple, and then so that little function affect all will apply for any state because it's generic in T. Okay. So now, imagine that you have yes, now you have a case where you have a method that you can, for example, call in the state check already or unknown, but not running, for example. So you change something, and so you call it either. How you do that? So that's interesting. Or you can do that. So let's conceptually see what we would like to do. We would like to do. So we start from the generic implementation, which apply to all of them. And we want to have a function, can be self or a reference or not, which do something, but only if T is either in the unknown state or in the ready state, but not no other state, right? Because conceptually, it's what we want to do. We don't do something when we are in that state. How we get that? Well, this notation here, remember we talk about trait at some point, and trait bound. So this is a trait bound. So this, in fact, tells us that we can define a trait. If we define a trait, unknown or ready, unknown or ready, an empty trait is just to indicate the compiler. And we say we want to implement the unknown or ready trait for the unknown type, and we want to implement it for the ready type. Then this method will work only when you are either in unknown or ready state. I'll let you think about that a minute. So that is very powerful. So the trait system, because a generic type can be, you can have a requirement. Sometimes I call that, but it's called a bound to it. That means it will check that the compiler will check that do something is called only for model of T, where the generic type T implements the trait unknown already. And unknown already is implemented only for the type unknown already. And I like it because I found it very intuitive. When I start by thinking how to do that myself, I started like, it's the way I started. Okay, I would like that. How can I do that? And then it strikes me, oh yeah, but it's a trait. So let's define the trait, and then that's all. Any question?
It's funny because it's an empty trait. I mean, nothing is implemented, but I mean, yeah, I think it's very flexible and neat.
It's a strength of a type system like the one defined for Rust, and for more and more modern languages are doing that stuff. You can really create implementation that where you can use also the compiler advantage, and that the check can do. So here is an example how the mechanism I use for model to define the sequence of steps to set up a model, and avoiding, so it won't allow us to compile the model, to compile a model if we don't use the method in the right state, or states even, because we can have several states. Okay?
Also, when the example you showed earlier, where you had all these function calls, like one on another, it would not compile if you had the order wrong, because the different functions return different kinds of models, and then you can't call a certain function on that kind of model, right?
Exactly. Okay. If we look at now the implementation of model itself, so you see it's going to be very similar to the example, but I wanted to start with the example because there's a new concept here before. But you see, effectively, I define the same step: model, unknown, ready, and completed. Okay, and on the model that we have, it's the same that in my example, model state. I have a few more information here, but the main thing I have my actors and my state, like I define. I keep track of when we start and when we finish the simulation, so I have that, and I can put a name on the model too, if we need. And let's keep that for now. And you see the same principle. Model unknown is where we define DV states the new model, and the check like we just did in example. I don't choose this example randomly. Effectively transition from unknown to ready. The same way. Here is where I redefine a new model, but the same data, but in the ready state. Okay. And then after that, you have ready documentation. It's where I call run, where I did run all the, I start all the thread. The thread are here using spawn. They are spawn here, and then it's where I move from ready to running here. Okay, the new model is running. So very similar to the model. Some important things to notice is that when you spawn a new thread, you need to move your actor in that thread, and here you lose access to it. Losing access to the actor is not really a problem because what really the information is really more in the clients. And remember, when you define your actor originally, you can decide to keep the client outside the thread by creating an arc container, and you can clone or you can really move it in the actor. So that's not really an issue here to move the actor in the thread and lose access to it. So that's why at that point, my vector of actors is set to none, because the actors have been moved into different threads that don't belong to the thread where the model is defined. But we need to wait for each actor to complete its task. So when you define spawn, in fact, return to you a handle to that thread, a kind of reference to the thread, and that's put into a vector task handle. So you see, originally, when I define the model new, I start with some actors and no thread handle because I was empty. But when you run the model, then the actors have been moved to their own threads. You don't have access to them, but you just have to access to the handle to the thread. So that happened. And then when you wait for the model, so here is a for loop here where we go through the different handle and we wait. The handles, you can wait for the thread. From using the handle, you can wait for the thread to finish. So it's where when you call the wait function, it's what it does. It goes through each of the actors and one by one you wait for them to finish. And when you turn the model completed, but if you look at it, the actors have been consumed and even the task handle has been consumed. So you have nothing left in your model at the end because it has been consumed. It has been done. So the model is again something which is transient, ephemeral. It just lasts for the time you need the model, and then most of the thing it contains are consumed and disappear. Okay. And then the two other functions that I have are name and flowchart. Flowchart. And you see, this is a case where it's also unknown already. But because when you are in the running state, you have consumed your actors, you cannot make a chart anymore because you don't have access to the information. That's why the question you asked, Christoph, was relevant. So I hope that makes sense. This little state space, state variable which are type parameters and with compile time error checks.
Yeah, one question. So with this model implementation, do you still need the phantom data because you have other data, or could you have done it without that?
No, you need. It's a requirement for Rust. If you define a generic type, then you need to have in your struct a variable of that type, or a variable of that type, or a type which is a derivative of that type, like phantom data. You have to. The compiler will throw that away. They told us, show documentation afterwards, that when you need that. Don't know why, but you need that. So we best want to stop here for today. So that's really what varies in model. And as I said, it's nice sometimes to split, especially after run, if you want to do something while the model is running. So I think we went through the whole implementation now of the framework, and there were a lot of things to go through because it relies on a lot of concept of Rust that we are not too familiar with. You know, we have asynchronous programming versus the containers like Arc or Mutex. There's the threat objects, and there's the state, and these little tricks with the state variable as a type, and how to transition from state to state using that, and how to have method which apply to multiple states and so on. So that's a lot of things around here. But I think that's basically, I think you have the whole, with this, I think 4 now session, you have we went through all the steps of building a model, I think. Any question? Okay, I'm going to stop here then. Stop record.